face the moment of truth. Here we actually get to see results. Thank you, Frank.
Okay, so this is work that really has been done mostly by Daniel Tolt and various other people. I'm one of those. It's been published in 3 papers, a lot of it, but the main results I'm going to show you are unpublished as yet. So the question that started this whole thing was, what sets the residual electron heat transfer in a barrier? And as you know, the standard view is we have strong equal speed shear flow and the long wavelengths are suppressed, you know, up to that drift wave question that you raised. And
what could be a null in the shearing rate? In which modes could that?
Yeah, exactly. So this is, and I'm going to come back to this in a second down here. We think that the ion heat flux is close to neoclassical, but the other channels we know to be anomalous. So what sets the electron heat transport? That's the question. Now there are some candidates to answer this question. One is paleoclassical transport, something put forward by Jim Callan, but it's disputed to say the least. Then there is the question, maybe there's residual long wavelength turbulence, drift wave ITT or something. That's unknown. And then there's the possibility of having high wave number turbulence. And this last possibility is what we try to investigate using gene simulation. So I'm not saying that, you know, we prove something. We just try to explore, is that third possibility, is that a viable possibility? Is that a candidate? So we focused on one particular Astix upgrade discharge at a particular time. It's an H-mode discharge, of course. Here is the safety factor profile. You might wonder about this kink, but this is what happens when you try to calculate the Q profile pretty accurately, taking into account bootstrap current effects. Usually this would just go up, but if you include the bootstrap current, then you get radial regions which are fairly narrow, but for which the global magnetic shear can actually be close to 0, even slightly negative, which is kind of amazing, so close to the separatrix. And here are some density and temperature profiles, and just to tell you where we are. So we're going to focus for the most part on this particular flux surface. Rho colloidal is, I think, 0.98. So we're somewhere maybe 2/3 up the pedestal. And then we take a tool that has been written by Pavlos Xanthopoulos from Greifswald. One version of it is called Tracer. A more general version is called GIST. It's documented in these 2 papers, and what it does is it takes an MHD equilibrium file, does field line tracing, and by this means it calculates all the geometric coefficients that go into the Gyrokinetic equations. So every time you have some differential operator in the Gyrokinetic equations and you write in general geometry, then you get some coefficients, and these are some of them. This is the Gxx, Gxy, Gyy, and as you notice here, they have very little, if not say nothing, to do with S-alpha geometry. So as you approach the separatrix, you deviate so substantially from what we used to for core turbulence simulations. Also from, you mentioned earlier, the parameters differ, the gradients in particular. Q differs, shear differs. But yeah, all of these geometric quantities differ a lot. And in some sense, I tend to think of this almost as a stellarator. You know, it's so wild that it opens up completely new possibilities for microinstabilities. And this is one of the field lines we traced. Okay, so this is what we get linearly for that particular case. Here is the growth rate as a function of the colloidal wave number. In red you can see the growth rates, in green are the real frequencies. So here is a hump at very low k, you know, it goes down to a ky rho I or rho s of 0.01. This is an ITG mode, and this little thing is a microtearing mode. We actually found in recent years that if you look at Astix upgrade plasmas, let's say the outer third roughly, that we get microtearing modes all over the place. So this is something that people have not looked at in great detail at the moment. Another student of mine, Hauke Dirk, is currently doing simulations along these lines. I mean, this little hump certainly wouldn't do anything, but in other cases, microtearing can be well in the game. And then starting already at ky rho I of about 0.2, you get the onset of ETG modes. You might wonder, what does ETG modes, what do they have to do at ion scales? But actually what happens is that the critical, as the temperature gradient is increased to values of the order of 50 or so, R over LT E, then the ky minimum, where the spectrum tends to peak, shifts down, and it actually shifts towards the ion scales. And it ends up, in this case, at a value of 0.2. So that's the linear spectrum you get in ky space. If you look at the same thing in kx ky space, you get a quite surprising finding. So the growth rate is color-coded here. The biggest growth rates you get at sufficient values or high values of ky rho s of about 10 and higher. But what's amazing is you get them for kx values, which are in the range of 60 or 80 here, which means that these modes are extremely tilted at the outward side. In the core, this would always peak in the middle, for reasons we have also mentioned last week. So this is very different, and this is one example that leads me to say that the geometry is so non-S alpha that one should really reconsider or rethink certain things one is used to. I mean, what makes stellar so appealing from a theoretical point of view is first of all, you have a lot of possibilities to control, a lot of knobs to control the transport from a practical point of view. And from a theoretical point of view, you have many new possibilities. For example, even in a simple standard W7X geometry, you can get dozens of ITG modes with adiabatic electrons. Not just one, but there's many of them. And the edge is not quite as wild, but it's still, again, very, very different from what we used to. However, concerning the characteristics of ETG modes, we still find that there's a critical eta E of the order of unity. And if we believe the measurements, and there's reason to do so, then the asterisks upgrade H modes usually have eta E values in the range of 1.5 to 2.53 or something like that.
Are you including shear flow in here or
No.
No shear electric field.
Well, what we actually do is, because to do the two-scale simulation ranging from 0.01 to 100, that's just not doable, even on the largest supercomputers. So what we do is we cut off somewhere here. We assume at this point that the long wavelengths are stabilized by shear flow, but we don't treat them explicitly. And then we just treat the small scales. And the idea is, because they will certainly not be affected much by shear flow. I'm going to show you a typical snapshot on the outward side of the vortices that you get. And I mean, they're very small scale.
So what are you doing? I'm not following. What are you doing about the ions then? Do you have a simplified description for the ions that you use?
Well, you can do two things, and we've done both. You can either assume that they are adiabatic, because you work at high K, then they're out. Or you can keep them kinetic. It doesn't change much. But on those scales, all you have is ETG modes anyways. The ITG modes are down here, 0.1 and below. And we don't treat this region at all.
Okay, but you have checked them kinetically.
Yeah. Okay, and this is what you get if you compute the resulting electron heat diffusivity in square meters per second. As a function of this eta E parameter, you get values between 0 and a little less than 1 square meter per second. And this blue region is the one where we think the experiment sits. So we tend to have eta E values maybe somewhat below 2 typically, and chi E, some part of a square meter per second.
Large as compared to experimental value?
No, it's what transport analysis seems to say. I mean, of course, it would not be easy to adjust, not be hard to adjust. If you would move just a little bit to the left here, then you could also go to smaller values. But transport analysis tends to say that these values are not so small.
So you said you have an R value of 50, right?
Yeah, roughly. And this is a snapshot of the contour plots of the electrostatic potential on the outboard side. From here to here, it's 1 ion gyroradius. You know, so such a structure is typically, maybe that's 1.5, that's maybe 0.5 gyroradii. So this is very small vortices. And shear flows would live on longer wavelengths. They would certainly shear apart ITG modes and the like, but not these small scale modes.
Those look like they have kx equal to 0.
Yep. And that's also captured here. To our surprise, we found that non-linearly everything comes back to a scenario that we're used to from core turbulence, which tends to peak at kx equals 0. So this is the heat flux spectrum color-coded. This is kx, ky. This is where we have most of the heat flux at pretty high ky wave numbers, but peaking around kx of 0. So everything is restored in the way we're used to. But this is a nonlinear effect. It seems that the modes that have the largest growth rates are not the ones as often. I mean, that's in general, it's something that we're used to from core turbulence, that the modes with the largest growth rate are not necessarily the ones that do most of the transport. And that's also happening here.
Sorry, can you give an idea of the residual Chi when the ions are non-negative, when they are left kinetic?
If it changes with respect to kinetic,
So, I mean,
can
when the ions are kinetically responding, is there a residual ion heat transport?
on these scales, not much.
On KY, because you start the spectrum case, it starts at KY smaller than 1.
We start at around 1.
Or you start at 1.
Yeah. And 1 and higher, there is not much. There's a little bit. We should actually move down a little bit further, maybe 0.5, 0.2 or somewhere in that range. And that's when you can get particle transport and also ion heat transport in principle. Yeah. Yep.
These are local gene simulations on the flux tube, or these are not local?
These are local simulations, and if ever there was a case where the local approximation is useful, then it's here, because we're working on 2 gyroradii or something. So even in the pedestal regime, this is a good approximation there.
Does anything special happen at the X point?
I'm going to come to that in a second. That's one of the questions that people raised. So my next slide was so far so good. So this is basically a summary of those 3 papers that already published. But people tended to pose 3 questions concerning that work. And the first one is, are you able to treat this complicated edge geometry correctly? There's a lot of discussions. You know, does one have to do special things to be able to approach the separatrix where everything diverges and goes crazy? And then this is just one aspect of it. What you can see here is a cross-section of Aztec's upgrade, and color-coded is the absolute of the local shear, local magnetic shear. The local magnetic shear tends to be negative. Maybe you can see this, there's a lobe here, this bluish border, and it encloses a reddish region, and everything in that region is negative local shear. And then there's also negative local shear actually further in the core. We're not maybe used to that so much, but of course the global shear further in is positive. But this is just one example of things that go pretty wild as we go out. And things become more and more non-S alpha. All the metric coefficients have very complex parallel structure. We have strong up-down asymmetry. We have strong local shear, especially near the X points. You get the largest values, which are yellow, down here. So the local shear can get as high as 50 or more. And of course, safety factor magnetic shear, global magnetic shear, diverge as we go out. So it's reasonable to ask, you know, can you do this with a standard gyrokinetic approach?
Is it negative or is it small?
It's
The black line is the 0 line.
Yeah. There's a little black line here. It's hard to see. You see, there comes a black thing. It's so surrounded by blue that you cannot see the black anymore. Yeah. Okay, so Here is, of course, Q and shear as you go to the edge. Shear diverges. This is the local shear. And for this particular position, so this is as we go along the field line once around poloidally, and the local shear, this is the position close to the lower x point, becomes larger than 20, then it goes down again, and so forth. If you do the integration of this thing, it turns out that the global magnetic shear is not terribly large, but the local shear can be very substantial over a narrow region. Something like this was often, as was often discussed in the stellar literature actually, is supposed to maybe localize modes. And then a mode that might want to live on the outboard side, extended like this, would be cut off by this region. And such an effect might be physical, but there's also effects that could come into play and cause numerical localization of modes. And this is something that Bruce Scott pointed out to us, and he was questioning to some degree if the kind of paralocalization that we got was really physical or not. So here is a picture from a paper by him from 2001. This is a sheared slab simulation. I think shear was 1 and there was no curvature. And still he got this kind of a heat flux profile along the field line. So there seemed to be some kind of ballooning, or there's no reason for the turbulence to balloon because we don't have curvature. And he pointed out that something like this can happen as you have high magnetic shear, for example, that you get spurious ballooning effects. And this could get in the way in our case. Now, let me try to explain where this comes from. If you have a mode that has kx equals 0, and you do this flux tube approach and you reach the parallel ends of your box, then you will connect it to a mode that has the same ky but a different kx. And every time you reach the end of a box, you do the same shift in kx. And when you do that, you come to higher kx's, which at some point will be damped. And so if you start with a mode, maybe I should go to the next page and point it out here. So, this goes from minus pi to pi along the field line, so once around poloidally. If a mode has kx equals 0, then you follow it up to here. And then when you connect back in Z, you connect it to this kx point. Then you move around here, and then you go the same step up again, you connect, and so forth. And the same on this side, the other direction. You can actually plug these together in the end, and you get a nice ballooning structure. Actually, ballooning type codes, GS2 works in this sense. You get one extended mode structure, which goes around poloidally several times. But you can also do it with just one poloidal turn by connecting adjacent modes. So this is the standard way it's done. But if you have a kx equals 0 mode, then it's fine. Everything is symmetric. But if you now have a finite kx mode starting here, then one of the connections would be here, and the other one would be here. And if you have, for example, some numerical dissipation in x or kx, then the two sides would suffer from an imbalance, or from an asymmetry. And this is what translates into such things. If a higher kx, non-zero, this is a 0 kx, this is a finite kx, then these guys will be damped a little bit. And if you do the superposition, then you get this humped structure, this pseudo-ballooning or spurious ballooning. So what was suggested by Scott was that one could, instead of doing the shift once every poloidal turn, you could do the shift after every grid point in the parallel direction. So you could divide it up. Instead of doing one big step, you do several smaller steps. And then you end up with such a situation. So you have a little bit of the mode sitting at this kx, another one at here, and a different z positions, different kx's. If you plug all of these guys together again, you get the same mode structure as you get here. So you have the same modes, but you shift them around in k-space. If you do this, then all your positions along Z are treated in exactly the same way. That's a nice feature of this thing. So you restore symmetry. And this is how it works out in practice. You might still have some damping, but if you have it, then it's the same everywhere in Z, and you don't get the spurious ballooning anymore. And to make a long story short, here you see simulations with standard metric in red and shifted metric in blue. The differences are probably mainly due to the fact that with shifted metric, you cannot use periodic boundary conditions anymore in the x direction. So we had to work with Dirichlet boundary conditions and introduce a damping zone. And this gave rise to differences in the range of 10–20%. So it's not serious, and all the qualitative features are the same. In particular, here is the electron heat flux along the magnetic coordinate, and you can see that the two have the same structure, and there is no numerical ballooning effect.
But isn't this just masking the problem?
In what sense?
Well, I mean, you don't see any ballooning, but there's still an issue of numerical resolution.
Oh, yes, yes.
So, I mean, to me, you're getting rid of the symptom. And so it makes it seem more comfortable, but I think the real solution is you can't get away without more resolution. Right?
That's a true statement in the sense that, I mean, shifted metric is not a miracle. I mean, it's an attempt to try to reduce the resolution requirements a little bit. But in any case, as you go towards the edge, your resolution requirements will go up substantially. Maybe this helps to limit them a little bit, but it will not save the day. In the end, you will still have to spend substantial resources, you're right. Okay, so a second question was, do you obtain strong ETG turbulence throughout the whole pedestal region? So one could say, you showed that ETG can explain the transport at 0.98. That was, let's say, 2/3 up the pedestal. But what further in or further out? Is it also possible to explain it there? And that's the outcome. This is the heat flux in megawatts as a function of rho poloidal. 0.96 is kind of where the pedestal top is. This is where the gradients become a little smaller and the profiles turn over. And these 3 points are in the pedestal region. And of course, there's some uncertainty about which eta E value to use. Here we use the nominal value that we got out of the database. But you could argue, is there a 10, 20, or even more % error on these? So you could probably well adjust these, but they're all certainly in the same ballpark and all pretty close to the experimental value, which is this blue line here. So this was the original point, and these 3 points have been added, and it seems that there is no dependence, no critical dependence on the radial position. And this is something that people have observed in the US, which people that try to use simple ETG models to put into their pedestal modeling. And some of these models were such that ETG transport either diverged or went to zero as you went to the separatrix, and this does not seem to be the case here.
Does R over LT, it stays the same despite the fact that R over LT changes a lot?
Eta E does not change dramatically, and R over LT changes somewhat, but not terribly. I mean, if you would have a temperature profile that would go all the way to zero at the separatrix, then 1 over LTE would diverge. But when you have a finite level, like 100 eVolt or something, then it will go up, but it will turn around and come back down again. It will not diverge to infinity. And then the third comment that was made is we know that in the core, Z effective or the temperature ratio can affect ETG stability. What if you take these effects into account? And this was done here. Again, the heat flux in megawatts as a function of this tau parameter, which is the product of Z effective and the electron to ion temperature ratio. It was shown in this particular paper that one expects for core type geometries, like alpha type geometries, that R over LTE critical does not depend on tau if you're limited by the density gradient. It does depend a lot on this parameter if the density profile is flat. But that's not the case here in the edge. So according to this formula, which comes of course from core simulations, you would not expect much impact. And here we changed this tau parameter by a factor of 6 from 0.5 to 3. And the heat flux changed by roughly a factor of 2 or so. Which means that there is some effect, but it's certainly not as dramatic as that it would shut off ETG or something. So these are the two main conclusions. ETG turbulence remains a strong candidate to explain this residual electron heat transport in barriers. And if this is really confirmed, then of course future simulations of LH transitions doing the full transition must include sub-ion scale dynamics, which is something people have been speculating about anyways for a long time, also for core transport barriers. So if you want to do the whole barrier formation, you would have to include these scales. And this of course makes it a very tricky thing because you have to include long wavelengths, the ion scales and sub-ion scales all in one simulation. But that seems to be the reality we have to face. Okay, that was my contribution. Thanks.